Another loaded week full of quantum mechanics. Let's see, we had our exam not too long ago, and we're just kind of on a roll now, aren't we? Not much to say other than let's do a little bit of a review, although I can't really say too much about last lecture because we just basically we've beaten this particle in a box thing to death at this point. I don't know how much more we could realistically do with that, or really what I could say in a review when basically most of last lecture essentially was a review, which reveals the process. I just want to point out that there's just kind of a mechanism by which this class will work from here on out, and we're just a little over a third of the way through the class, so this should help guide you. We're going to be spending still most of the class on quantum mechanics with a little bit of kinetics at the very end. So while we're on quantum, which again is most of the class still, everything is going to come down to stating a problem. The problem will be like the free wave problem, the particle in the box problem, today the finite box problem, the infinite step potential problem, the hydrogen atom problem. Usually these are defined by the potential energy. We have some way of solving the wave function, whether we just use some horse sense about it like we did with the particle in the box, or could be done with the particle in the box, or we use boundary conditions. That's what we're going to do today. Sometimes coming up when we get to harder problems, it turns out that some geezer from the 1800s had solved the math equation, not knowing it was quantum mechanics, of course, but solved the exact same equation. And of course the solution is the wave function. And because this is an 18th century math class, I will often, obviously I'm just going to tell you this is where I got it. I got it from an 1850s textbook, and seriously, that's a lot of the answers coming up next. Answers being wave functions. With wave functions, we'll normalize them, blah, blah, blah. Apply the Hamiltonian and get the energy. Now, usually we're going to have multiple energies. We have a ground state and excited states. It's amazing how often that comes up, which you know that molecules have ground states and excited states. The ground state of the hydrogen atom is the 1s state. The excited states are the 2s and 2p, 3s, 3p, and 3d, blah, blah, blah. Those are all excited states. You can do spectroscopy, knowing those energies. All right, so there's a lot we get out of that. We can calculate momentum, position. We can use those to look at uncertainty principles. Uncertainty principles do things, so it's not just an exercise in like, well, I can calculate this, therefore I will. Not that that doesn't happen, but again, you've seen plenty of examples of how the uncertainty principle has meaning. Then there's some interpretation. So why do quantum dots work the way they do? Why do those signing dyes work the way they do? And again, as we get into more complex models, we're going to have more sophisticated interpretations, things that are, I hope you find a little bit more interesting, things that maybe you've never heard of. So there's that. All right. So this is what I'm doing in lieu of a review. Not much to it. I'll be a little bit more review-y-ish in future lectures, but we have this kind of like this clean break, having reviewed the particle in the box as closely as we did and gone into every like little minutia that we could possibly go into with that. Since we did the particle in the box, then God, this is a heavy-handed figure, isn't it? Then we talked about the particle in the finite box, which is what we're going to spend most of today's lecture on. Okay, so one of my little pet peeves, and it will appear on an exam in some form, is to note that this, I know this, I didn't do the greatest job with this. I think I need to get a new color pen. But this is 4 graphs in one. All right, graph number 1 is the potential energy. Energy is the y-axis, and x is the x-axis, position. All right, now kind of the heavy dotted line, I've drawn the finite box, right? So that goes on forever to the left, forever to the right. It's a particle in a box, except it's finite. The potential, the trap is finite, which is way more realistic than the infinite box. The infinite box is easy to solve, though, and it has those applications that you saw. Okay, there's 3 more graphs. Remember, these are all like graphs drawn on cellophane, on plastic, and overlaid with each other. Graph number 1 is the ground state. Wave function looks a lot like a particle in a box, like a half sign, sorry. half sign, except that it spills over the edges. Which makes sense because it can, right? It doesn't take an infinite amount of energy to spill over to the sides like the particle in the box did. Remember, this is the particle in the finite box. Okay, I'm showing the first excited state just for the heck of it, so it also basically looks the same, but it also spills a little bit out of the box a little bit. These are called the bound states. That's important. And that means that when we calculate their energy is less than V naught, where V naught is defined as how, God, for lack of a better word, how tall the potential is, how deep the trap is. Okay. Now I've drawn, our fourth graph is an unbound. That is an unbound wave function. All right. Now I think it's not hard to see that, a couple of things. Energy is greater than V naught, and I only have so much room on the board. It's very wavy in the trap because it has all kinetic energy, but it loses some kinetic energy when it moves to the right or to the left, because it loses that kinetic energy to the potential energy. So it has a longer wavelength, a longer de Broglie wavelength. I hope I've drawn that well enough, and it keeps going and going and going. It'll go forever. And the same is on the left. If the particle escapes the box and it moves to the left, it'll just keep going to the left forever and ever. And let's see, it has some kind of neat meanings, and I'm going to get into a little bit more detail. You could imagine that this is like an electron, and this is like the 1s state of a hydrogen atom. So this is the electron in the 1s state, the ground state, and this is like a 2s state. Well, the thing is, if you really zapped a hydrogen atom, you could do that by sending an arc of electricity through a gas chamber full of hydrogen gas. You would rip the electrons off. Well, that's what an unbound state would be. That would be the electron just saying, sayonara, I picked up a lot of energy and now I'm gone. So we're building up something that is kind of like a model for an atom, and it includes ionization of the atom. Atoms ionize. So, as I mentioned, as we build up sophistication, we see more and more realistic representations of phenomena that we're familiar with, and now we're getting a quantum mechanical view of things. Another one is that, remember that the quantum in quantum mechanics means that energy comes in discrete steps. So if I was to do spectroscopy on this particle in a finite box, I would see a peak corresponding to this energy difference. The energy difference, of course, being determined by the Hamiltonian, which I mentioned to you. That's how you do spectroscopy. Okay, in terms of how many, what are the discrete states of the unbound particle or electron, whatever, there's an infinite number. As long as the energy is greater than the potential, it can have any energy. Again, any energy, so long as it's greater than V naught, is allowed. So there's actually an infinite number of unbound states. So I'm just drawing one of them, obviously. So that's a little detail. Don't worry about that so much. I just wanted you to know that, but there's not much I can do with it. But there you go, you have it now. Okay, now for the rest of this lecture, we're going to talk a little bit about how you solve this. Now this is a little funky. We're not actually going to do it. Solving these wave functions via boundary conditions, the boundary conditions will be smooth and continuous at the boundaries of the finite box, so we're going to apply smooth and continuous boundary conditions. From those, you can determine the energies, you can determine the wave functions, you can determine the energies, everything. However, what we're going to run into is an algebraic nightmare. So here's what I'm going to do. I'm going to show you how to solve it, and then stop. If you want to look at the actual derivation, then there's a handout on the website. Okay. I don't want to spend 20 or 30 minutes doing algebra, because that's actually what solving this problem takes. Instead, we're going to take the lessons on how to solve this and apply it to a simpler problem called the infinite step problem. And then we're going to also do the finite step problem, finite barrier problem. Same thing. Anyway, that's coming up. We're going to do the infinite step problem at the end of this class, and the finite barrier problem will be for next class. So those will use the lessons on how to solve this. Now to solve this, I need some more room here. Now again, while I'm not going to actually do all the bloody math, what I'm about to show you, we're going to apply several times. You're also going to have a homework if I haven't assigned it already, because I'm a little confused because I'm actually doing, this is being filmed 2 weeks in the future, by the way, so I'm not exactly sure what I've assigned for homework yet. So sorry about that, COVID, this, that. It takes me a long time to do the effects, by the way, especially you're going to see some neat digital effects today and tomorrow. And those I spent 2 or 3 days on them, so that I need some lead time. Anyway. So what I'm about to show you, please take note of it. All right, I know I said that I'm not going to actually finish this derivation, but please take very close notes to what I'm about to do, because you're going to be doing this several times. This problem, the other paradigm, the other problems I talked about on your homework, and I'll have questions on the exam that are like this. All right, so step 1. All of these problems are defined by the potential surface. We're still in 1 dimension, so that's nice. Okay, so again, I'll define potential energy, and here's x. So I'm just redrawing what I did before. It was kind of a bloody mess, right, what I had before. So I just need a little bit more of a clean space to work with. Goes to the left and right for infinity. All right, regions 1. I'll use Roman numerals 2 and 3. These are flat potentials. Therefore, the wave functions are e to the I kx and e to the minus I kx. We've talked quite a bit about that, so you should definitely know that. So, what do I want to do here? Okay, so let me go ahead and define the wave functions, okay? The wave function in region 1, what is it? A, e to the I. Now I got to be careful. K1x. All right, now remember that K are wave vectors. They're 2 pi over the de Broglie wavelength. And you just saw me make those drawings. It was very clear in the Unbound case that we're going to have different wavelengths on the left and right versus the middle. That means they have different Ks. So K1 plus B. And remember, e to the I kx, b e to the minus I kx, k1x, is always true for flat potentials. Now notice what I'm going to do here. I'm going to write the same thing down twice more. Except that, hold on, a, b, c, so the coefficients won't necessarily be the same. Oh, and state 2, region 2, has k2. D e to the minus I k2x, k2x. In region 3, 1 second, A, B, C, D, E, I'm going to cut that. E to the, too many E's, I k3, no, k1, k1x. I bet you thought I was going to say ik3x, it's ik1x. I'll explain that in 1 second when we just finish. Okay, so again, you can't assume that the letters are the same, so A, B, C, D, E, F. Now, K1, K2, K1, K1, K2, K1. The reason that regions 1 and 3 have the same K value is based on the definition of K, which I'm going to write down in a second because I bet you forgot. But ultimately, it's because this potential is fully symmetric. The left side is identical to the right side, like if you just folded it over, right? They're the same. You may be thinking, well, no, left is left and right is right. That is a word in English. It doesn't mean anything to nature. Nature doesn't know left from right. That's your sense of how to order the world, but nature doesn't see it that way. So given that the left and right side are completely identical, regions 1 and regions 3 have the same K value. Now, if that argument doesn't resonate with you, I'll write down what the definition of K is in 1 moment. Okay. Next bit, and this is one of the things I hate about quantum. I hate doing this, but let me tell you some things here. Recall when I was talking about, especially like the Unbound case. I said if the particle in this finite box gets to moving, let's do region 3, if it gets to moving to the right, it'll keep going. It'll keep going forever, because if it's going to like come backward, it has to have run into something. So there has to be something else out here, but I'm not going to let there be. Again, if the particle gets out of the box to the right, it will keep moving to the right. So why would I have a left wave, right? The E wave is a right wave and the F is a left wave, because that's either the minus IKX. Minus IKX are left waves, plus IKX are right waves. There is no left wave, because the particle can never move to the left. Now, one of the things I don't like about what I just did, I mean, I like it that it's simplified, but what I don't like is I'm doing derivation by logic and not algebra or calc. I mean, to some of you it may be like, well, that's way better. I find it somewhat unsatisfying, but that's just me. Okay, what about region 1? Okay, if the particle is moving to the left, it will continue to move to the left forever, so there's no reason to have a right wave. Okay, so we'll get rid of this part. All right. It's nice that it's simplified, it's just that I don't like doing derivation via mechanisms that don't involve derivation. I think you see what I mean. Anyway, doesn't matter, these are our wave functions. Okay, now again, you got to be able to set this up using the same logic I just did, but look, it's really easy. The thing moving to the right is a right wave, the thing moving to the left is a left wave. This is the part that, again, you're seeing this for the first time, and you gotta get this. This is one of the times that you're seeing something new, and this is like a thing to be learned. First thing is, how do I do this? I'm going to do region 2 and 3. The wave functions have to be continuous. That means at region 2, at x equals L, it better be equal to the wave, the region 3 wave function at x equals L. Okay, so that's kind of easy, right? I mean, that makes sense. I hope that makes sense. Remember we talked about the second lecture of quantum, how wave functions have to be smooth and continuous. Okay, so now I got to look at this. Okay, region 2 is C e to the I k 2 to L plus d e to the minus I k to L equals C e to the, no, E, it's an E. There's a C there. E I k 1 L. Okay, I swear to God I hope I did that right. Okay, so there's that. Now you may be thinking like, well, what do you do with that? The answer is nothing. It looks like, now that I've written this down, it gives me a little bit better idea of what am I actually trying to do. Notice that it's kind of easy to just start writing things down but not see the big picture or the end goal, especially when you're doing a lot of algebra, which is what we're doing. The end goal will be to define K1 and K2 and A, B, C, D, E, F. Well, sorry, there's no A or F, but anyway, B, C, D, E. Okay, so we've got 4 unknowns, B, C, D, E, and K1 and K2. So we have a bunch of unknowns. If we have unknowns, what we need are a system of equations to solve them. X plus y is 1. X minus y is minus 1. X plus 3y, right? Remember those, 9th grade or something? Okay, so that's actually what I'm doing. The system of equations is determined by smooth and continuous. Now, hopefully you remember that. So I've talked about continuous, now let's do smooth. And I'm hoping that you remember this symbol. Oh, sorry, little Roman numerals have to have a top. Yeah. Little dash, right? Now you remember that. That means derivative, right? Derivative of the wave function at region 2 at x equals L has to be equal to the derivative of wave function 3 at x equals L. Okay, the wave functions are equal and the derivatives are equal. So you can imagine that the connection between the wave function on the left and right of this part, at this part, you wouldn't be able to see like a seam there. It's just like smooth and continuous, right? Anyway, okay, so what's this? ik2 e to the ik2c. I should really look at my notes. I'm going to try to wing it. Minus ik2d e to the minus ik2l equal to ik1e e to the ik1l. Okay, now, next thing, and we're going to apply this next thing to all the subsequent problems that we actually are going to solve, but not this one. I think you already see that this is going to get kind of hideous. So what you do next, you make what's called I think it's a log derivative boundary condition. I think that's the proper thing. What that is the derivative over the wave function in region 2 is equal to the derivative over derivative over the wave function in region 3. Okay, now why am I doing that? See, I got to get it just right, or the world will end. There we go. Why am I doing that? Hold on one second, you're going to see. Okay, so notice that I've already written the derivative on top, so now I'm just going to write the other thing on bottom. I'm just writing that same thing over again. Okay, now remember that the end goal is to set up a system of equations. X plus y is 1, x minus y is minus 1, solve for x and y, that thing. When you do it this way, you simplify things, and that's pretty awesome. Okay, so what have I got over here now? Now you're going to see it right here. See that? You see how I've eliminated the e? I've eliminated that. And look at that, e to the ik minus e to the ik. I can remove all the i's, and e to the ik minus e to the minus ik. That looks like a sine function. And e to the ik plus e to the minus ik, that's a cosine. So it looks to me like I've got a tangent here. I've got a tangent is equal to k1. Okay, now look at the handout, and you'll see how I go from there. I'm not going to do anything more with it because it gets bloody awful. I also have too many unknowns, right? You may notice that I've got C, E, K1, and K2. I've got no E. I got rid of E. Anyway. You then have to do this for the other boundary at x equals 0. A little easier because the exponentials go away. Then you've got enough equations and enough unknowns that you can solve it. And again, it's done in the handout, 2 pages of algebra. So you see why I'm not going to go further. But this is the mechanism. So big picture, solve by boundary conditions. The boundary conditions are smooth and continuous. Smooth, you do smooth divided by continuous, and it just simplifies things that you then do some algebra and get the energies, the wave functions, yada yada yada. You want to see this done? Look at the handout. It's unpleasant to be blunt, and there you go. This is, I'm actually just doing this one, mostly because I had introduced this in the last lecture, so I kind of feel obliged to talk about it a little further. There's 2 more things I'm going to tell you about it here in a minute. But when it comes to doing this to completion, we're going to work with some simpler models, right? So I guess maybe I'm just not doing this in the best order possible, but I did what I did for the reasons that you know I just did. Anyway, okay, 2 more bits about this. I'm going to show you a neat little interesting thing about the Ks, K1 and K2, and then I'm going to tell you a little bit more about how to interpret these finite box models. Okay, so I have enough room to talk about the Ks, and then I'm going to have to wipe out the board, and I've done some computer animation so that you can see a little bit about what kind of information we learn from finite boxes anyway. Okay, next bit. Oh, actually this is kind of useful. All right, notice how the wave function, if it's in a bound state and it's off to the right of the potential, we'll just look at region 3. It just clocks out, right? Why is that? Okay, so let's look at region 3. So region 3, that's the E wave. Okay, now I want to tell you some things about K1 in this wave function. K1, now hopefully, I'm praying you remember this. We did this, if you've forgotten, on the first day of quantum mechanics, Monday, week 3, Monday of week 3. I started talking about K. K is the wave vector. 2 pi over the de Broglie wavelength. You saw how it gets incorporated into like cosine. Remember, cosine was our first wave. We're still dealing with cosine anyway. Hopefully you remember that it's 2me over h bar squared, except here we have E minus potential, right? Potential is just a number. We're in region 3, so we're in a potential region. And remember, I said a zillion times that the potential just kind of just takes away energy, right? Remember, it's just a number. Energy is just a scalar number. Remember that word scalar? So is potential energy. 2me over h bar squared, except we just have a different E. How different? In the bound case, V is greater than E. And if you get confused, just because I swear to God I do this too, insert a number. 3 minus 7 is minus 4. Oh, this is negative. Why does that matter? Because you got to take the square root of it to get K1. Because the wave has K1 in it, not K1 squared. And if you're going to take the square root of a negative number, you got yourself a bit of a problem, an imaginary problem. So tell you what, let's do this. I'm going to take the square root of this jazz, but I know I'm taking the square root of a negative number, so I'm going to make it a positive by taking an I out of it. But now that means that the interior has to be positive, and I'll do that by switching the positions of V naught and E. Now, by the way, I know that what I said is very hand-wavy, but it's actually rigorously mathematically correct in terms of my algebra. So these things are completely consistent with each other. I just factored out a minus sign, but since I factored out a minus sign under a square root, I took the letter I outside the square root. Okay, so what? Watch this. E to the, too many E's. I squared. Well, this jazz, 2v minus E. Should speed up time, maybe. Let's call that e to the minus k. I'm going to redefine k1 as this. Okay, so there you go. Ta-da! So what? Well, they don't even look different. E to the k1x, e to the k1, hold on. E to the I k1x, and we know that that's a wave. E to the ix is sine and cosine, right? We've been doing that for like a month now. E to the minus x, that's not a sine or a cosine, that's just an exponential decay. This is that, right? No sine or cosine, it's not wavy. There's no letter I in it. It's just exactly what, when did you learn about exponentials, right? It's that. But now, look at this right here. You see? Exponential decay. So that's where that comes from. Anyway, I just wanted you to remember how this works, and now you see why this looks the way it does. Last bit, the left one, let's figure out what, here, I want to be like orderly. In region 1, you would have, what is it, a B wave? It would be e to the plus k1x. If you go through that rigmarole, you'll get e to the plus k1x. Now that's an exponential rise, so it seems like there's a bit of a problem. E to the minus x, plug in numbers in your graphing calculator, it's just a decay. But this is a rise. I could ask a question on your exam. Resolve this. Look at the graph. The region 1 is left of 0, right? The B wave is only left of 0. And going that way, more negative, e to the, it is negative. The minus sign is hiding inside the x, because the x, the b wave is only to the left of 0. X is always negative. There's your minus sign. So this is an exponential decay, just like right here. Okay. All right, folks. I know this was a little bit of a handful. The main thing is I got one more thing to show you about this, but just to summarize the mathematics is, again, the procedure that we use, some stuff about k's and why wave functions decay exponentially when they're in bound states. Try to remember this. You know, I try to make sure that sometimes I tell you, this is a detail, don't worry about it. This is one of the times I'm telling you, you need to get this inside of you and keep it till the end of class, right? All right, so I told you about how to solve it, what the k's are, showed you a couple of examples, and to make it really solid, again, I still feel bad about this. I know we didn't actually solve this, but in the next hour, we're going to just work with a simpler system, and we will solve it, and it'll hopefully, the whole thing will kind of make a lot more sense. All right, but to do that, I need to wipe out the board. So give me one moment to do that. All right, so I've done some computer graphics here, and the reason I've done that is to not only give you a little bit of a better figure, because my drawings can be kind of limited sometimes, but also because the drawings, the renderings I'm about to show you, generated on a computer, are the exact quantum mechanical solutions to the potential surfaces that I'm showing. Now, what I've done is I've used some special mathematical techniques that we're not covering in this class to do so. Regardless, these are, what I'm about to show you, you're not seeing them yet, these are the solutions to the potential surface that you see here, where what I've done is I've got a finite box on the left, and then I go a little bit over to the right and I draw another finite box, and they're exactly the same thing. So that little bit of finiteness between them is what I've labeled as a barrier. Okay, so I mean that's kind of sensible, right? I mean, yeah, I mean I think it's kind of easy to understand what you're looking at. What is maybe not so clear is that I can make an analogy to this potential surface and say that, like, the trap on the left is an atom, and so is the trap on the right. So these are like two atoms, and they're the same atom, and they're right next to each other. What about the particle in the finite box? Well, let's make those electrons. Why is there a trap? Well, again, they're atoms, and the trap then represents the Coulombic interaction with the nucleus. The electron likes to be near the nucleus. That's a very good interaction. And so that's why it's downhill in potential, and it's like a trap. Now, the electron can escape the atom, which we've just talked about, and when two atoms are right next to each other, what could they do? There's like two carbon atoms, two hydrogen atoms, right? Hydrogen comes in the form of H2. Okay, so what I've done is I've made a very crude model of an atom. Okay, so this is the potential surface. Let's look at the first wave function. This is the ground state wave function. And what you see is basically just the ground state that I just showed before on the left and right, but notice the in-between space, in the barrier space. You notice how the wave function doesn't drop all the way to 0? And notice that there's a finite amount of area there. So that's highlighted. What does that represent? Well, the wave function represents the probability that you're going to find, again, these particles are electrons. So what I'm seeing here is that the electrons may bunch up between the two nuclei. So what is that like? That's like positive, that's the trap, negative, here's the electron, positive, that's the other atom. Positive, negative, positive. Well, that's very sticky by Coulomb's law, right? Electrostatics. Positive, negative, positive is a stable thing. That's, the negative is like glued to the positives. What I'm saying is, this is a bond. You're seeing quantum mechanics tell you what bonding looks like. It's when electrons bunch up between nuclei. Now, these little traps aren't the greatest models for atoms. We are actually going to do that. We're going to do a hydrogen atom. Regardless, you're starting to see a little bit more, as we get into more sophisticated models, you're seeing more sophisticated interpretations of them. Let's raise our game up a bit. Here is the first excited state. I've squinched them down so that I can put them into the same graph. Okay, here's the first excited state. Now this one, the wave function on the right is positive, and the one on the left is, the one on the left is positive, and the one on the right is negative. And so that means that the in-between has a node, right? So I've labeled that. Now, if you're going to have the wave function cross zero, that means that the area in between, inside the barrier, is way less than what you see in the ground state. So again, the first excited state has a node between the two traps, and therefore the amount of wave function in between is way less than what you see in the ground state. And I think that's obvious from the figure. Now that means I've got positive, nothing, positive, positive, positive. That is not stable. Two positive things are going to repel each other. Well, that's like an antibond. But now, haven't you had enough organic and freshman chemistry? Ground states tend to be bonding, and if you put things in an excited state, they tend to be antibonding. Well, that's what that looks like. I can even raise the level up a little bit more. Imagine like conjugated systems where the excited states can be complicated. Let's look at the second and third excited states. Here you can see that the second excited state, we see a return to a bonding pattern, and in the third excited state, we see actually some more like antibonding. So we see like there's a progression of bonding, antibonding, bonding, antibonding. Now, I don't know if that's realistic, but again, we're starting to develop our quantum mechanical knowledge to look at really sophisticated things like bonding between atoms. Okay, so that's all I really wanted to say about that. And I hope you enjoyed the graphics. I'm going to have some really cool graphics coming up here shortly. And I normally don't spend that much time on the finite box, but again, I learned how to do those calculations actually not too long ago, those wave function calculations. So I just wanted to show off a bit. I got a couple more coming up soon too. Okay, so no more finite box. As I mentioned, the way the class progresses is we're going to have like model system, paradigm. They have names, the free wave, the particle in the box, the particle in the finite box. Here's our next one. It is the infinite infinite step. The infinite step. So these are all potential surfaces. We're still in one dimension. So let's plot potential energy on the right. We have x is our axis, and we're going to have a step. The step goes on forever to the left and right, and it has a height, an oomph of v naught. Okay, so notice that it's basically like half a box, half a finite box. This guy we can solve. Let's, for convenience, you know, it actually really matters what you call like 0 and L when you solve these. It doesn't change the result, it just like is going to be way easier. In this case, making x, the step at x equals 0, that makes things way easier. Don't call this x equals L, call it x equals 0, or you will regret it if you don't. You'll see that in a minute. Okay. Now, I think I actually have enough time to solve this. All right, but what am I trying to solve? Well, I'm going to have regions 1 and region 2. So again, it's already a little bit easier than the finite box. So this is why I can actually solve this one, and I want you to see that. And okay, so then I can define wave functions. I can define wave function in region 1 and a wave function in region 2. And we're going to have like A, B, C, D, and e to the ikx and e to the minus ikx. But here's the thing. I need to make some stipulations on what's going on. And I know it sounds strange, but what do I mean? Okay, so remember how I mentioned that the free wave is great to start learning quantum mechanics, although it's a really flawed model because it represents a universe with nothing in it except a particle, and it's only one-dimensional, and there's nothing in it except the particle. Easy to work with, massively unrealistic. There's really no interpretations you can make of it. You're just learning quantum mechanics. Okay, now I have to set up this universe too. And so let's say that the great turkey in the sky who can create universes created a one-dimensional universe with a step. But now it gets a little bit more complicated. The great turkey picked up, let's say it's an electron, picked up an electron and threw it at the barrier. Okay, so I have to make that stipulation. Now that means that in region 1, we've got ourselves an A wave, right? A forward, and it'll have K1 of K, e to the I K1x, right? So that's the turkey, the great turkey, by the way, not just a regular turkey, picking up an electron and throwing it at the barrier. All right, now, with that said, it's going to be kind of easy to imagine that maybe the particle penetrates into region 2, or it'll bounce back and scatter backward. And what I'm drawing here is kind of the traditional representation. And I've got some cool graphics you'll see, I think maybe next class. Okay, now hopefully this all makes sense, right? Well, not the stuff about the great turkey, but I think you get it, right? So there's an A wave because the turkey threw an electron at the barrier, but it could bounce back. And that means that the proper word for that is backscatter. So if it bounces off the wall, then I need to have a B wave. And that's what's represented here. So this is the A wave, this is the B wave, and so there you go. So it's moving forward, but it might bounce off the wall and go backwards, so I need to have a backward wave. Now, of course, let's make this the C wave. The C wave, if the particle gets through, it will do so. Now we have a different K because we looked at how we define Ks. K1, of course, is square root of 2me over h bar squared. K2 is in a region of potential 2me minus v naught over h bar squared. Of course, you're going to get different behavior if energy is greater or less than v naught. But you know that, but we'll get to there in a minute. Okay, so of course, region 1 and region 2 have different Ks. I hope that's obvious. Again, forward wave, it could bounce off, but if it happens to get through the barrier, and it will need more energy than V naught, just heads up. I think it's kind of obvious, right? If it has enough energy, it will move to the right, but there's nothing to backscatter off, right? Because I'm not like drawing another step. I could. I'm not going to do that. I could draw another step, but I'm just going to keep the potential flat at V naught. If the C wave can get past the barrier, then it's going to keep going, and so therefore there's no reason to have an e to the minus ik2x because there's nothing to bounce off of. So these problems sometimes require a little bit of storytelling to set it up properly. Let's see, now, it looks like I'm running out of time, so let me, I guess I could just end there and then just tell you a little bit about how we're going to set this up, which of course is we're going to have region 1 equal to the wave function at region 2 at x equals 0, and of course we're going to have the derivative at x equals 0 equal to the derivative in region 2 at x equals 0 as well. Okay, from this, we're going to be able to define everything, right? All the A's, B's, and C's, and all the K's. That's what we're going to get out of this. Okay, so, yeah, like I say, it's a little bit early, but, you know, I think, again, I actually promised you that we would be I didn't want to fill up all 50 minutes because normally in class there's questions and, you know, stuff happens, and it's not really... I mean, I kind of want to use the entire time, but I know it's not really quite right to do that because it's, you know, I'm kind of taking advantage of the COVID situation. So just remember this for next time. On Wednesday, we're going to do the algebra to solve this. It's very, very easy. And I'm going to have a whole bunch of videos for you as well. I got 2 videos. I worked several days on them, and they're really neat. They're going to show you, I actually have a movie of this happening. I have a quantum mechanical movie showing you what happens when a wave hits a barrier. All right, so I've talked too much, and so we're going to get a little bit early. I will see you all on Wednesday.